right? So we will see some examples for linear transformations. More precisely, we have to figure out whether a transformation is linear or not linear. So for linear transformation, there are these two properties that we have to show, that the transformation can be applied term by term, and that the scalar multiple can be factored out. Or we can combine together these two properties and just show property 3, where we have a sum and then each term is multiplied by scalars. And then we show that in one step we can do it term by term and factor out. Well, it's really not one step, but it's one line that we show. This property 3 is just a combination of the first two properties to show that something is a linear transformation. It's a choice. It's a matter of style to choose which one we want to try. But for example, the second one looks shorter, then it might be more complicated still, because we have to work with 4 different things. We have to work with the 2 scalars and the 2 vectors. And then the other thing is that in some cases we have to show that something is not linear. And in this case, if one fails, then it's already not linear. Or if only 2 fails, usually both of them fail, but it's enough to show one of them fails, and it's already then non-linear transformation. Or if the third one is not satisfied, then the third property, then it's also non-linear transformation. So in some cases, actually, it's especially if we want to show that something is not linear, then we might just start, for example, with property 2, and if that already fails, then we don't have to continue. But if that is, for example, satisfied, then we still have to check the first property, and if that fails, then again it is not linear. So let's see some examples. The transformation, linear transformation example, or in some cases it will be not linear transformation. We have to figure it out. So in this example, T, it maps from 2 by 2 matrices into 2 by 2 matrices. And the formula is that T of A equals SA S inverse, where S is a given matrix 3, 5, minus 9, 0. In fact, this doesn't really matter. Well, it matters that the matrix S should have an inverse that you might want to check, but otherwise it doesn't matter what the specific numbers are. And in fact, even the size of the matrix doesn't really matter. So since this is given, you can consider this as a constant. Then when you see this formula, S inverse, that means that it maps, it assigns to the matrix A another matrix S inverse. Some basic matrix algebra you have to remember, or you have to review from undergraduate linear algebra. For example, that the multiplication is not commutative, so you cannot change the order and cancel S with S inverse. If it was just a 1 by 1 matrix, which means it's a number, then we could do that. Still, I would recommend to try to think of this as just one variable. Like if it was an X, and then you say that it's S times X, S inverse, which is the reciprocal of S if it's number. And these are constant numbers. Then you see that this is basically just constant times the variable X. So this is only true if we have numbers. Right now we don't have numbers, but you still should remember that this is the function Cx is a linear function. So this suggests that this might be linear. So let me start with property 3. Try to show that this is linear in one step, the original one with matrices. So the variable is A, and the vector element. So property 3 was that C times U vector plus D times V vector, and T applied to this, can be taken apart, and this is C times T of U plus D times T of V. Now, instead of U vector in vector space U, we have a vector, which is really a matrix, but it's considered a vector in the vector space of the 2 by 2 matrices. Since a 2 by 2 matrices is a vector space, that means A is considered a vector of this abstract vector space. So then this property written with matrices, the scalar field is still the real numbers. When we work with matrices, we multiply it with real numbers. So then we can still use the C notation, but for the U and V vectors, I will use A and then D times B matrix notation. Capital letter stands for matrices. Then from here, we would like to get to this other side to take it apart, but first then we have to write a definition of this transformation. So the argument is used in this definition by multiplying it from left and right with S from left and with S inverse from right. So we have S from left and then CA plus DB argument and then S inverse from the right. Again, we need, as I mentioned, basic matrix algebra properties from undergraduate linear algebra. So for example, the matrix multiplication is distributive, which means that we can multiply through the parentheses. So we get from the left S times CA plus S times DB. Let me do it in 2 steps, from left first, and then from the right, S times CA C inverse plus, again from the right now with S inverse, DB S inverse. And remember, the matrix multiplication is not commutative, you cannot change the orders. Matrix multiplication from left has to stay from left, and from right stays right. Then another property is a scalar multiplication of matrix multiplication, that this can be brought in front. C times SA S inverse and D times SB S inverse. And then if we check the definition of the T transformation, we get C times the transformation applied to the A matrix plus D times the transformation applied to the B matrix, which is exactly what we have to show. The fact that we didn't use any special thing about C and D means that this is true for all CD real number, which is the scalar now, and for all matrices that are the vectors now. So that means this transformation is linear. Let me also practice the writing of the notation of the vector space of linear transformation. So L denotes the space of linear transformations since it maps from R2 by 2 to 2 by 2 matrices. That means it maps into its own vector space. We don't have to duplicate U and V, we just write the vector space of 2 by 2 matrices. So this is a linear transformation on the vector space of 2 by 2 matrices.